So today we're going to be solving a material and energy balances problem with a continuous stirred tank reactor. So if you look at our problem that I've pulled up for us here, we see in the first sentence CSTR. That just stands for continuous stirred tank reactor. So we can see here, our problem gives us a lot of information. We're going to be using this information to come up with differential equations involving the concentration of A and the reactor temperature T. But before we get into all that, I wanted to explain this problem a little bit more and give you guys a drawn diagram of what it's going to look like so you have a better idea of what we're dealing with here. So we're going to have some kind of tank, and it's going to have some liquid in it. If we look at our parameters here, it looks like we have only one volume, so it's going to be at a constant volume. And it's going to be continuously stirred. There's my stirring rod in there. And it's going to have some concentration going in, some concentration going out. We see it's going to be an irreversible first order reaction, A to B. Let's see, it also says we're going to have a jacket on our tank. So if you're not familiar with what that is, it's not very complicated. It's just, in this case, it's a coolant jacket. So it's going to be cold water flowing in, cold water flowing out here. And that is just basically going to cool down the contents of our tank. If we see here, it says it's going to be exothermic. So that means that our reaction inside of our tank is going to be releasing heat. So the coolant jacket is just to keep our contents from not overheating and potentially exploding. So also, if we look down here at our parameters, we see a negative delta HR. That's also an indication that it's exothermic because delta HR is the enthalpy or heat of the reaction, and the negative in front of that indicates that it's going to be exothermic. So, like we said before, we're interested in finding the concentration of A and the reactor temperature T. So it's going to be the temperature inside of our tank. And what else does it give us here? Two cases are simulated, one based on increased cooling by changing TC, the coolant temperature, from 300 Kelvin to 290 Kelvin. So we're basically saying if we were in some simulation where we decreased the coolant temperature from 300 Kelvin to 290 Kelvin, how is that going to affect our concentration of A and our temperature inside the tank over some period of time? So that's going to be our start of our differential equations. So that's the change in concentration of A over some time and the change in temperature inside of our tank over some period of time. And it looks like we also have it in another situation, increasing 300 Kelvin to 305 Kelvin. So if we look at our parameters that were given over here, we can see we have a Q, and that's in liters per minute. So we know that Q is going to be our flow rate in and out of the tank. Since we're only given one flow rate, we're just going to assume that our Q in is going to equal our Q out. Next, we're moving down, we have the CAI term, and you're probably wondering if that's initial or incoming concentration of A. But if we look over here, we have the CA of 0. So we can assume that one is going to be our initial concentration of A because it shows our initial temperatures of inside the tank and of our coolant. So our CAI is going to be the incoming concentration of A. Moving down, we have this TI. That's going to be not the initial temperature, but the incoming temperature. So we're going to have some T going in and our T going out. Sorry, T going out is just going to be our same temperature inside our tank because it is a CSTR. I'm also going to write our Q in and Q out the same. And here we see our volume again is 100 liters constant. Our density is 1,000 grams per liter. So that sounds like the density of water. And we're going to assume that it's going to be constant. And assuming that the concentration of our A coming in isn't going to affect the density inside our tank. This C down here, it's going to be, if we look at our units, joules per gram Kelvin. So that sounds like heat capacity. And since we're only given one, we're just going to assume that it's the same for all components. And then again, our delta HR, negative delta HR, exothermic. Then going over to this next column, we have this E over R and a K naught. So if you are familiar with the Arrhenius equation, the Arrhenius equation has some reaction rate equal to K naught, which is the Arrhenius prefactor or frequency of collisions, multiplied by the exponential of negative activation energy over R, which is just a constant, times temperature. So our E over R is going to be the same in here. It's going to be our activation energy over that constant R. And then our K naught is going to be the frequency of collisions. So we're given that one also. So we can rewrite this with our known numbers in here. So we have 7.2 times 10 to the 10th reciprocal minutes times our exponential. And so we have a negative sign in front of our activation energy, so we need to include that. Negative 8750 kelvins over the temperature. So for the Arrhenius equation, it's going to give us a gauge of how much temperature is going to have an effect on the frequency of collisions. So if we think about it logically, mathematically, if you have a really high temperature with like relatively normal activation energy, you're going to have E to the 0 power, which is just 1. So the frequency of collisions, K naught, is going to be equal to the reaction rate. So that just basically means every collision is going to cause a reaction. And that's a really important thing to be aware of. Also, if you were to have a really, really high activation energy, then your rate of collisions is really, really going to be dependent on temperature. So now we can go ahead and say that our reaction rate for the concentration of A is going to be equal to our K from here times our concentration of A inside the tank. And that's because it is a first order reaction. And again, it's going to be dependent on temperature. And you're probably wondering how can that be dependent on temperature when we'll use the rate for A in this equation? And we also have this other differential equation that's dependent on temperature. And luckily, we are given this UA over here. And that's going to be the overall heat transfer coefficient multiplied by the area. So another way we can explain that is that our UA will be equal to the heat transferred from reactor to coolant. So heat transferred from reactant to coolant. And if you look back at our situation here, we know that hot air transfers to cooler air. So the heat is going to be flowing out of inside of our tank to the coolant on the outside, which is what we want, so that the coolant jacket will cool down the inside of our tank. So we need to say the temperature inside of our tank minus the coolant temperature to account for that. And our UA is going to be in 5 times 10 to the 4th joules per minute Kelvin. All right. So I think now we can go ahead and start coming up with our differential equations. And get rid of these right here so we have some room. So now we're going to begin coming up with differential equations to solve for our change in concentration of A and our reactor temperature T. So always when we're thinking about material and energy balance equations, we have the same idea for every type of problem. It's going to be some type of accumulation is equal to what is going into our system, subtracted by what is going out of our system, and also subtract any rate of consumption inside of our system. So remember, we want to find our change in concentration of A over some time, so we can express that as the differential of concentration over time. And this is going to be in units of moles per liter. And we want this to give us a value in mass over some time. So we have that pesky liters in there, but luckily it gives us a volume in liters. So we can just multiply this by our volume, and so we're left with moles over time. And this is going to be the rate of accumulation for A, the whole left side of our equation. And now moving to the right side, we want to think about what's going into our tank. So we're given a flow rate of Q equals 100 liters per minute. And again, we're going to want some units of mass over time. So if that's liters per minute, we want it to be some mass over minutes. So we can actually multiply our flow rate by the concentration of A going into our tank. So that will give us moles per minute. And since our flow rate, we're assuming, is not changing, we're going to use that for going in and out. Thinking about what's going out of our tank with regards to the concentration of A, if we have our continuous stirred tank reactor, CSTR, the concentration inside of our tank is going to be the same as what the concentration of A leaving our tank is. So that's just going to be minus our Ca. Now we know there's going to be some rate of consumption of A because our reaction is going from A to B. And that's actually just going to be our Ra equals KCa down here. We found that earlier. That's going to be our rate of consumption. So we'll just subtract KCa. And now the units for our rate of consumption is in moles per liters seconds. And again, we want mass over time. So to get rid of that liters in the bottom, we can multiply by volume again. So the next thing we want to do, since we want to get our equation equal to our change in concentration of A over time, we're just going to divide the whole thing by volume. So we'll have the rate of change in concentration of A equal to our flow rate divided by volume now, times the concentration of A going in minus the concentration of A leaving our tank, minus our K times Ca, which is the rate of consumption. And this is going to be our first differential equation for finding the rate of change of A over some period of time. So the differential equation we just found with respect to the concentration of A is our material balance equation. So now we want to find our energy balance equation. Because we're dealing with a liquid, we can use enthalpy, the heat of the reaction equations. We're talking about internal energies. So in our system, we have internal energy going in, internal energy going out. Because we are using a liquid, the specific volume of a liquid is going to be extremely small because liquids are fairly dense. And if you remember, if you're familiar with the enthalpy equation, you can look it up anywhere. It's going to be internal energy plus pressure times specific volume. And we're going to be assuming that the non-flow work coming from our spinning agitator in here inside of our tank is negligible because nothing's mentioned about it in our problem, so we're just going to ignore that. So in this case, we're going to be assuming that the internal energy and enthalpy are basically going to be the same. So we're going to be using an equation of enthalpy, which you might recognize from high school classes, is delta H, which is change in enthalpy, equal to mass times specific heat times change in temperature. So again, we're going to be using the same principle of material and energy balance problems where accumulation is equal to what is going into the tank minus what's going out of the tank minus what's being consumed. So if we're thinking about our accumulation in this case, that is actually going to be our change in enthalpy, or delta H. So if we think about what our mass would look like in our problem here, we're not given an exact mass, but we can solve for it in a way because we are given rho, the density in grams per liter, and the flow rate Q in liters per minute. That would give us units of grams in the end, which is mass. So we'll have our Q times our rho. And C, the specific heat, is given to us in the parameters, which is just C. And then our delta T, we're going to write it as our change in temperature with respect to time. So just to check our units, we're going to have Q as liters per minute, rho as grams per liter, our specific heat as joules per gram Kelvin, and our change in temperature over time is going to be kelvins per minute. So our liters cancel, grams cancel, and kelvins cancel. I'm sorry, I made a mistake. This should not be rho. It should be, I'm sorry, it should not be Q, it should be rho, because density times volume equals mass. My mistake. So we'll have grams per liter times our liters. So then liters cancel and grams cancel, and we're left with joules per minute. And that's exactly why you check units, to make sure you don't make any mistakes like I just did. So in our concentration of A over time equation above, we wanted everything in grams per minute or some units of mass over time. In this case, since we're doing a energy balance, we want some kind of energy over time, which is our joules per minute. So we're good there. Just gonna erase this to give us some more room. And this is going to be our left-hand side of the equation, our rate of accumulation. So now for our right-hand side of our equation, thinking about what goes in minus what goes out, we're going to have some enthalpy going into our system and some enthalpy going out. So we'll just write it as H in minus H out for now. And then we're also going to have some heat that's being transferred from inside of our tank to the coolant layer outside. So we can represent that as subtracting the heat transfer, because we're losing that heat to the coolant on the outside. The coolant is cooling the tank. And then also, because our reaction is exothermic, we have our negative 8 delta HR. There's going to be energy that's being generated from heating of the system. So we're actually going to want to add that. So we'll add our exo just for now. So we can go ahead and substitute some variables that were given for our H in, H out, and heat transfer and exothermic, so we can use the variables that were given to solve this problem. So thinking about the enthalpy going in and enthalpy going out, we can use the same principle of delta H equals M times C times delta T. We have our flow rate going in and out of our tank that are equal to each other. So our Q. And again, it's volumetric, so we need to multiply by our rho, our density. So we're looking at units over here. We'll have liters per minute times our density of grams per liter. So we have right now grams per minute, but we also need to multiply by our specific heat and our change in temperature. So C, it's just going to be C. Change in temperature for what's going in is going to be our T flowing in minus our temperature inside the tank. And we're given our temperature going in over here in our parameters. So that's going to be Ti minus temperature inside the tank. And again, T going out is going to be the same as the temperature inside the tank because we have a continuous stirred tank reactor. So checking our units again, we have joules per gram Kelvin, and temperature is just going to be kelvins. So liters cancel, grams cancel, kelvins cancel, and we have joules per minute. So we are good there. I'm actually going to bring this other side down here. All right. Fix this a little bit. Here we go. So now we have our H in minus H out. This is our equation for that here on the right side. Next, we want to account for the heat transfer. So our coolant is going to be actually absorbing some heat from the reactor. So that is just what we found before. Over here, the heat transfer from reactant to coolant are UA times temperature minus temperature of the coolant. So we'll just rewrite that again over here. Oops. All right, and I believe the units of that are already in joules per minute, so we don't need to multiply that by anything else to get the correct units. And now for our exothermic reaction part of the equation. So we're going to be adding this. And so we're given the negative delta HR in our parameters. That's a positive number, so I'm just going to write this as negative delta HR. That is the enthalpy of the reaction. And that is in units of joules per mole. And we want joules per minute. So what we're gonna do is multiply by our rate of reaction of concentration of A, rate of reaction constant K times concentration of A, which is in moles per liter times minutes. So now we have joules per liter minutes. We also need to multiply by volume to get rid of that liters. So we'll have moles cancel, liters cancel, and we're left with joules per minute. Alrighty, now I think that means we're good then. All of our units are correct. If we take a minute to look at our equation here, we can see that if we were to increase the concentration of A over here, since we are adding this part of the equation, if we increase the concentration of A, it's going to increase our change in temperature over time. Because we're adding it on there, concentration increases, that means temperature is going to increase as well. Also, if we were to have a big difference in our temperature inside of our tank and our coolant temperature, it is greatly going to decrease the change in temperature over time because we're subtracting that from our equation. So it's pretty cool to see how this equation can represent different changes and can predict what the reactants and temperature would be inside of our tank. So now, again, we will want to have our change in temperature over time alone on this side of our equation for coding, but we can worry about that later. But I think we're ready to go ahead and start coding. So now we're ready to begin our coding. I've already started our code a little bit, imported numpy, scipy integrate as solve IVP function, and plotly subplots. Because we're going to be using those throughout our code. We're going to be using the solve IVP because we have our differential equations. And then I've also typed up all of our given values that were given in table 2.3 of our problem. Before we get started, I wanted to note that temperature is going to be a big factor of our equations because our Arrhenius equation, K here, is going to be reliant on temperature and determined by that temperature value. And then our K is going to be used in our concentration of A over some period of time. So it's going to be dependent on temperature in our material balance equation. And also for our energy balance equation, we have our K value in here also. So to begin, we always define our function, and we want the right-hand side of our equations. The independent variable is going to be time, and dependent, we'll just say y because we have two dependent variables in this case. So we can unpack our y. we know that concentration of A and our temperature inside of our reactor are going to be the dependent variables. And let's see, our return statement is going to be the right-hand side of both of our equations. But since we have that K value in both equations, we need to type that up first. So K is going to equal our K naught, which we have up here. K naught times, we need to use numpy exponential. And again, it's going to be negative of our B, which we already calculated as our activation energy over R. So that's just going to be divided by our temperature inside of our reactor. And then we should be able to go ahead and type up our right-hand side of our differential equations. So I've typed up our two differential equation right-hand side of our equations here, and it looks good. So now we can go ahead and use our solve IVP function. And make that like that. First thing we need is to define our function, which is going to be our right-hand side. We need our time span. So we have from 0, and I put a time end up here as 10 minutes. So we'll just type t end. Then we need our initial values. So for our independent variable initial values, we need to supply our initial concentration of A. Ca naught, and our initial temperature. And then the method we're going to use is going to be the same that we've been using, the Rideau method. And then lastly, we just need our dense output to be true. And we just want the solution of that. So there we go, we got our solution to start plotting. All right, so before we begin plotting, I wanted to define this solve IVP as our solution. And then we also need to supply some kind of time frame. So we'll say our t-plot. This is where we use our lens space, and we need to supply beginning time, end time, which was our t end, and the number of intervals. So we'll say 500. And then the next thing, before we can make our plots, we need to separate and define our independent variables. So that's going to be equal to our solution with the dependent variable of our t-plot. So now we can go ahead and make our fig subplot, or I'm sorry, make subplot. And because our two dependent variables are going to be, they're going to have different units, we need to make two columns for that. And we'll just use one row. All right, so now we can go ahead and type out our plot information. So fig, add scatter. Our x is going to be our t-plot. Y, we can start out with the concentration of A. The mode we want to use is lines, so we can see that relationship. We want it to be row 1. We want this to be in column 1. And I like to give it a name so we know which one's which. So we'll call it the concentration of A. Then I'm just going to copy and paste this down. and then make a couple changes so we can do the same for our temperature. So this is going to be our temperature inside. It's going to be column 2. I can change the name. All right, so we can see we've got our 2 columns. The blue one is our concentration of A, and the red one is our temperature inside of our reactor. So let's talk about what these graphs actually mean. So we can see on our graph to the right here, our temperature is decreasing greatly, which makes sense because we have the cooling jacket on our tank to cool down our reaction. And if we think about our Arrhenius equation, if temperature is dropping, that's going to mean that less A is going to be reacting because our K value is going to be really small, which is going to make our reaction rate really small. So if we started with our 0.5 moles per liter of A and the concentration in the tank was supposed to be around 1 mole per liter, we get really, really close to that, 0.95, and it kind of plateaus. So not a lot of that A is going to be reacting. The next temperature change we wanted was to go to 305 Kelvin. Here we have a big change, and this is not going to be good because our heat is spiking a great ton up here. That's because it's an exothermic reaction, and if we're increasing the temperature of our coolant, it's not going to be able to cool our reaction down very much. So as our reaction rate is going to be increasing as heat increases, we can see that almost all of A is getting reacted over here on our left graph. So all the way down to 0.0117 is how low it gets. So almost all of our concentration of A is going to be reacted. But as this happens, because there's not much A left to be reacted, our temperature is going to begin to cool down again, and then it's just going to create this back and forth reaction process. So this just shows the importance of simulating these kind of reactions, especially for exothermic reactions, because if this were to be actually executed in a lab, there could be explosions, people could be harmed, and that would not be good. So it's just really important to simulate these type of reactions before executing them, just to for safety reasons and also just to better understand how your reaction is going to work. So hopefully you enjoyed this video and the process of using material and energy balance differential equations to find these kind of relationships.